be here. It's a pleasure to see you all, and I'd like to tell you a little bit about our research. And I think this is a great conference for me to see how the information technology is being used and applied in many different fields and different areas. Even this morning, we saw how the technology is advancing and how it can be used for better communication and interaction with the elderly, and many other really great ways that the information technology can be used. What I'd like to tell you about is some of the work we've been doing in taking the information technology and its use and applying it in better exposure assessment and epidemiologic research. So the challenge in environmental epidemiology is identifying people and where they are in space and time and how that may be related to their risk for disease. And so if you can think about over your life course, how if you develop a chronic disease, either heart disease or cancer, is how can we identify your short and long-term mobility and how that's related to your exposures to certain environmental risk factors, health behavior, how does it link with social factors maybe on the geographic scale. And so some of the work we'd like to present with you is how, and then linking, then once you take this information, and I as an epidemiologist can apply it to disease risk assessment, but then how can we work together with biostatisticians like Dr. Rathman in terms of actually modeling the spatial time distributions to better quantify that risk, okay? So what I'd like to do today is give you some research background and then give you some examples. And at the workshop tomorrow, we'll go through other examples. I'll give some examples, maybe some of the details about geocoding and taking the geographic information. And then Dr. Rathman will spend a couple hours in terms of actually doing some of the biostatistics and the modeling and some of the software that can be used to do this. So in the workshop, we'll give you more details. So some examples on breast cancer and bladder and rectal cancer, and then I'll mention a little bit about work with a geography student on using hierarchical Bayesian modeling to look at spatial temporal patterns of lung cancer. And then I'm going to skip the next one. I'll do that more in the workshop, so I'm not sure if we'll have enough time. And then Dr. Rathman will describe how he's developed some of the statistical modeling to apply to one issue, which is groundwater, uranium, and radon exposure in the home and how it's related to breast cancer. So what is spatial epidemiology? It's the analysis of spatial and geographic distribution of the incidence of disease, but then also it's taking spatial hypotheses and doing disease mapping, ecological analysis, look at disease clustering, and for me, it's not only just using at the ecological or just current residents, but for me, it's within the context of analytic epidemiology is how can we take residential history and other exposures and combine them to look at spatial time clustering. Okay? So what is GIS? Well, now you all have the GIS in your car. It's terrific, right? And you can find out where the local store is or the market or whatever, right? Well, what's really fantastic now is that you can capture, store, and analyze and present data linked to a specific location. You can do queries, you can take and add it, you can do map creation, you can result the presentation, but it's not only mapping, but other information that a GIS can do. So we can take multiple layers. For example, if we're interested in a certain geographic location and how long you live there, we can actually take the location on a map. We can look at the water, groundwater contamination. We can look at air pollution modeling. So we can take multiple layers and apply it to the same geographic space. But not only that, we can do it for every specific time period over however long we can collect the data, right? So fantastic. So we can combine data sources. We can link the multiple databases. We can visualize it. Right? We can turn it into spatial information that can then be used analytically, so not just visually, but analytically, and we can do interactive maps and many other things with a GIS system. So it's handling large and various data sources. It can be used for analysis of different types of data using spatial analytic methods, and we can integrate it with other information. And the applications in public health are immense, right? So in public health, mapping is just one area. So in mapping, we can map populations at risk. Where do they live? How long have they lived there? We can look at spatial patterns of disease over the geographic space. We can look at spatial temporal trends. So not only, so as epidemiologists, we're really interested in, is the disease going up? Is it going down? Over what time periods? We can actually visualize areas where the risk is highest, and I'll show you some really good examples of how we can do that. And then we can use it to not only mapping, but analyze spatial analysis and modeling exposures to environmental factors. So actually modeling the environmental factors, as I said, taking all of the data over the space and in different times, and you can stratify these different risk factors. You can detect disease clustering. There are many biostatistical approaches for assessing this type of clustering. A really big thing now, especially in the United States with the Obamacare, right, is the access to health care and delivery of health care services. So it can be used for that as well. You can also use the GIS for intervention and prevention. You can do infectious disease surveillance and control, outbreak investigation. You can look at resource allocation, monitoring disease interventions over time. So if you have an intervention in a certain geographic area, you can track over time to see what happens. So really, use of GIS can be, Geographic Information Systems can be very good. Well, in around 2000, there was interest in integrating use of GIS in public health sciences. And so I worked with the geography department. At that time, I was at the University of Buffalo. And we developed a grant to the National Institutes of Health, and we got funded for a 5-year period to develop methods in geography and to apply them in epidemiology. And so spatial temporal GIS analysis for environmental health was the project. And what we did is we were interested in developing what we called geospatial lifelines, which was the taking someone where they lived on a plane, right, on a geographic space, and monitor over the course of their life course where they lived. And then Fred moved, and he was over here, and then he moved back, whereas John went this way, and then he moved over this way, and then, you know, many different locations. So how do you track that over time, and are there certain windows of exposure that you're interested in? Okay, and so we developed a study of breast cancer. And with breast cancer, is the part of the issue is we don't understand. Only the classic risk factors only explain about half of the breast cancer risk. The rest is kind of unexplained. And so we were interested in looking at environmental risk factors, in particular at early life. So we developed a study which was based on the case control method. So for those of you who aren't epidemiologists, is that you select on disease, right? And so, and you take people who don't have disease and people who have disease, cases and controls. Then you go back in time and you explore all the exposures that have occurred over their past. So, and you can go back even to when they were born and ask them where they lived, what did they eat, where did they go, common exposures, and you have to ask carefully. So what we did is we developed a lifetime residential history called, and it was for the Webb study. So it was Western New York exposures in breast cancer. So we took women 35 to 79 years old in 2 counties. We collected cases and controls over a 5-year period. And controls were randomly selected on age, race, and county of current residence. And for under age 65, we got people without disease from driver's license and over age 65 from Medicare. And so we randomly selected and then asked people to come into our center for detailed in-person interviews, self-administered questionnaires. One of the things we did is before they came in, we sent them a form and asked them to fill out their lifetime residential history, where they lived. They could look up records or whatever and say, okay, where were you born? And then for every residence, where did you live? And so then what we did is we wanted to use this residency as a proxy of exposure. And so so we had about 1,200 breast cancer cases and something like 1,800 controls. I can't remember the exact number. So we had quite a few, right? For all of those people in the study, we had 20,000 addresses, right? So one of the nice things about GIS is you can take these addresses and you can then geocode them, and I'll talk in the workshop a little bit about how to do that. And then We were interested in residents at birth, residents at the time of their menarche, and then also 10 and 20 years, and then also the current residents. So we used their residential history, we geocoded it, and then we could locate it on the space. So I'll give you some examples. We did geocoding, so that process of linking records in two databases. And so there's preparing, geocoding, reviewing, and evaluation. There's address matching steps. I'm going to go through this quickly. We can go over this in the workshop, where you geocode and you can do batch and interactive with the software. So there's software available to do this. And then we looked at how well we did. So for the 20,000 addresses, for the two Erie and County addresses were 15,000. So people stayed in the area. You know, they weren't too mobile, right? And addresses for the 6 temporal groups, the different time periods we were interested in, were about 14,000. So 92% we total matched. With batch matching was 85%. So that's pretty good. So the computer matches it if you have a good address. 6.9% interactive matching, and we were unable to match only, unmatched were 7% of the addresses. 6% had incomplete addresses. So it's important to really get at the address, right? So if you have a P.O. box, you can't geocode a P.O. box, post office box, right? So that's part of the problem. So I'll tell you a little bit about, we wanted to look at air pollution and breast cancer. So this was Matt Bonner, who was a doctoral student. And we were interested in polycyclic aromatic hydrocarbons. So here's the numbers. 1,166 women with breast cancer and 2,000 controls, frequently matched on age, race, and county. And we were interested in their exposure to air pollution. So we got the air pollution exposure from 1959 to 1997. So they had monitored air monitors over the geographic area. We got each one of those monitors, and we could estimate the exposure to air pollution over that geographic space. And then we took each woman, and we used ArcGIS 8.0, right? And we used unconditional logistic regression, and we wanted to look at their exposure to these air pollutants. And we used the logistic quadratic spline regression to look at modeling the risk. And so this is this is Buffalo, New York. This is Lake Erie. And here, these are the two counties. And these were the birth addresses. So just the address at the time of birth of the women with breast cancer and the controls. Okay? And so is exposure to particulates at these different time periods associated with risk? Here's the total suspended particulates for the 1960s. Buffalo was a very industrial, a lot of steel plants and refineries, and they were all along the water, and all the people lived here. So you can see this dark spot is the wind would just blow the pollution right into the place where people lived, right? And so here's what we found is that for postmenopausal breast cancer, we found a significant dose-response relationship between the air pollution exposure at the time of birth and your risk for breast cancer. And it wasn't as strong for premenopausal. And it's adjusting. One of the nice things about a case control study, you can adjust for all the known risk factors for breast cancer: age at menarche, benign breast disease, purity, body mass index, family history. Okay? Everybody follow me so far? So we were able to use the geographic, right, residences, and that this one happened to be just looking at birth. Here's the risk, the odds ratios. You can see that it increases for increasing level of exposure to air pollution, and the P for the significant trend. And here's the modeled total suspended particulate data. This is for postmenopausal women. And postmenopausal breast cancer is really a different disease almost than premenopausal breast cancer. It has a different risk factor pattern. It has different, so heavy women get postmenopausal, whereas skinny women get premenopausal. So you have to look at them separately. So here's for postmenopausal where we found more of the risk. Here's premenopausal. See this weird risk curve with regard to, and this is at the birth address. I won't show you the other data. We looked at cumulative exposure, which also was significant, but it appeared that early life exposure was the most important. So if we just took the current residence of where someone lived, we would have missed the whole thing, right? So exposure, especially at birth, was related to risk. Another, working with geography and the methods, just to give you, for those of you in the biostatistics area, Daekwon Han was a doctoral student in geography, and he developed a method to look at clustering. So he took all of the addresses, every single one of those 20,000, and he looked at the cases and controls with regard to space-time clustering. Okay? And so this is what he came up with. This is premenopausal cases, right? And this is the controls. And this is all of the addresses over those, over that time period, right? Over the many decades, right? And then he did a statistical analysis, which I'll explain. So we use this spatial temporal variability to look at the risk surfaces, right? And the surfaces compared pre- and postmenopausal women from the 1940s to the 1990s. So he actually could take over those decades and then look at where the cases lived relative to the controls and look at for the geographic spatial clustering. In the paper, in the book, there's a little methods paragraph that explains how this was done using the K function. So we were able to pinpoint geographic areas that had higher risks through this special spatial analysis. Another geography student worked with me on a case control study of bladder cancer, and we had these points where we had trihalomethane in the drinking water over, this is in Rochester, New York, so each of these dots had a measured level of this pollution, and so he used kriging to actually come up with a risk surface for different types of contaminants in the water. So here's bromodichloromethane chloroform. Total 551 is a mutagen in the water. So this is related to adding chlorine for disinfection, right? So what we are interested in is here's the distribution of the residents for the cases, and here's the controls. Is how did this exposure pattern relate to the residents of the cases and controls and risk, right? And so what we came up with was that this total 551, which was a composite index of cancer-causing chemicals, was related to an increased risk of 2.34. And then we were able to adjust for diet and smoking and all of these other risk factors. Okay? So using the GIS, we could come up with this exposure across space and time. What's really interesting, too, is that the concentrations of these chemicals were at the end of the distribution system. So the longer the water stays in the system, if you're at the end of the distribution system, the higher the exposure levels. Okay. Bromoform had almost a threefold risk. So 3 times the risk if you lived in an area on that map where the bromoform exposures were higher. Okay. We also did the same for rectal cancer. Whoops. And here's the risk patterns for the exposure. Here's where the rectal cancer cases and controls lived. And here's the so this is a nice thing you can do in terms of displaying over on a map, is this is the risk surface, right? So this is the actual odds ratios displayed on a map, and the bigger circle means that there is higher risk. So this area here tended to have a higher risk. So you can do all kinds of really interesting stuff, right, with regard to this. How are we doing on time? 20 minutes left? 40, okay, we got plenty of time. Okay, so I'm going through this stuff quickly. Is everybody following me so far? Okay. So once you identify where people live and how long they live there, and then you can use this to just take any of the exposure estimates that you can get with colleagues in the health departments or regional local health departments or any place where they measure some of this stuff, right? And come up with estimated exposures. So for trihalomethane levels, they varied spatially within the county. Again, bromoform, increased odds ratio for rectal cancer, again, was 1.85, so almost 2-fold risk, which was significant. Highest quartiles of estimated consumption of bromoform led to increased risk. And then there was marginal with other trihalomethanes. So levels of these THMs had spatial variability that was partially due to the variation in the water age and the geographic pattern of increased risk in areas with the highest level of bromoform in the county. So that's another example of a case control study. And then most recently working with a geography student at the University of Georgia, he came to us and he said, I'm really interested in lung cancer. And so we had the lung cancer data, and we had all of the lung cancer cases from 2000 to 2007 in Georgia, and we actually had the residents at the time of diagnosis. So it's not as good as the lifetime residents that we had in the case control study. But he wanted to model the patterns, spatio-temporal patterns of lung cancer over time. And so the study purpose was look at the spatio-temporal pattern of the lung cancer incidence. So incidence is the number of new cases of disease that occur. So it's not death or mortality, although for lung cancer, usually the 5-year survival is very low. And so, so usually mortality is a good indicator. But the best thing that we like to use in epidemiology is incidence, the number of new cases. And so here in Croatia, you have a very nice cancer registry. And so the cancer registry data in Croatia, you could do stuff like this, you know, similar stuff. Yeah? Yes. Yeah, it's not just the number, but you have to look at the rate, right? The standardized incidence rate of disease per given population. Yeah, so you have to have the population counts as well. So, so we wanted to look at difference. He was interested in looking at socioeconomic status on the risk of each of the population subgroups. So the study design was looking at 2000 to 2007, and then you had the population strata by race and gender in each of the geographic areas throughout the state. And then we had the geographic information also from the Comprehensive Cancer Registry combined with the census data. So we wanted to model the relative risk of lung cancer. And of course there's health risk behaviors that you're interested in, but health risk factors, but we had measured variables. So he actually wanted to take a geographic-based measure of socioeconomic status and try to look at, and also space and time, and look at these fixed effects. And he also developed methods to look at these unobserved variable, looking at random effects of space and time and space-time combinations. And so here's his model. I'm not sure if can you read that in the back? But so he wanted to compare 5 joint models and 2 separate models using deviance information criteria. And so the autocorrelation is considered in the priors for all spatial and temporal random effects. So the final model using this joint mapping is you wanted to calculate the relative risk at the log scale, and he incorporated a SES effect or socioeconomic status effect based on the data that he had for each geographic area. And then he used the shared spatial random effect, and then a specific spatial random effect, and a specific spatial temporal interaction term. And so he used the census tracts. There were 1,618 census tracts, and he also wanted to look at the time period. And so this was used to, again, then model the standardized incidence rates and how they may be related to space and time. So, so this is for 2000, 2001. These are the standard incidence rates for each of the census tracts across Georgia. This is for white males, this is white females, black males, and black females. So he developed a race and gender specific model. And then this was the relative risk from the modeling for 2000 to 2001. So here's 2000 to 2001, again, for white males. So you can see that there's certain geographic areas that have higher risk for each of the different groups. And here's the elevated relative risk for each census tract during 2000 to 2007. Again, so he could do it for each year, and then he could do it for averaging across all of the years. Now, one of the things when we converted it to PDF was that I had a little animation that showed you for each year the change in these colors for each gender race group over the course of each year, each 2-year period, 2002, 2004, but it didn't work when we converted it to PDF, so, versus PowerPoint. The conclusions were that Bayesian modeling with shared components makes smooth risk maps by borrowing strengths from neighboring regions and time periods as well as population groups. And then what we found is that Northwest Georgia had stable, high, elevated lung cancer incidence rates over all age, race, sex groups. So it was this area here, which is the upper part, these upper parts in this northwest area, that tended to have the higher incidence rates. And it just so happens that that also coincides. We're going to do further modeling, and Steve is going to explain some of the stuff we're doing with cancer incidence, looking at radon and uranium in the groundwater and how it's related to risk. So that'll come up in a second. Yeah. These are all controlled. Yeah, these are all controlled for age and other factors, right? And socioeconomic status and other stuff, right? Yes, effect on lung cancer incidence is a large gradient in males, especially white males. So he was interested. There's stuff that I didn't show, where he was interested in actually looking at the socioeconomic status in each of those geographic units and how it may be related to risk. We didn't have smoking data. So again, this is kind of an ecological data, but you assume that the smoking variable is equally distributed across the geographic areas, right? And that would improve the modeling. If anything, lack of having the data would tend to drive it towards the null. So anyway, that's some of the work that the geography student did, taking some of the cancer incidence data and used Bayesian modeling to come up. Now, how much time do we have now? Half an hour. Okay. So I have now. I'm going to quickly go through some of this. If you have questions, I can go over. One of the other things that we did with another co-author is Dr. Wagner, who is an assistant professor in my department, and we were very much interested in looking at incidence, but also the mortality to incidence ratio. Well, what is that? The mortality incidence ratio is the age-adjusted mortality cancer rate divided by the age-adjusted incidence rate. It's also called the fatality ratio, or it's fatality which adjusts for the incidence level. Okay, so we were interested. It's almost like a survival type measure, right? And we were interested in looking at this over geographic space and time, but also for different racial groups in Georgia and gender groups. So we wanted to look at racial disparities in cancer outcomes. So in the U.S. blacks have 25% higher mortality than other races for all cancers. So the disparities are very large. They have more aggressive tumors. But incidence is usually higher in blacks, but not always. So a good example is breast cancer, where the incidence rate in black women is lower than white women, but the mortality rate in black women is higher than for white women. Okay, so we calculated, looked at cancer incidence mortality data for a 5-year period, and we looked at all sites combined and the leading cancers, which were lung, bronchus, colorectal, female breast, oral, cervical, and prostate. We did National Center for Health Statistics population estimates, and we calculated these mortality incidence ratios using directly age-adjusted rates. Okay, and then we mapped these mortality incidence ratios. So we mapped them and compared the geographic health factors for each of the county health districts. Okay, so what's really nice is you can take different kinds of rates, and you can again use the geographic display to kind of look and see if there are certain patterns that you may see that are related to risk. The health factors, behaviors that we had at the county level were tobacco use, diet and exercise, alcohol use, unsafe sex. We had clinical care, access to care, and quality of care measures. Socioeconomic status at the county health data district, education, employment, income, family and social support, and community safety. And we also had an environmental quality index, or the built environment. So we had these measures at the county level. These weren't at the individual level. But we had the incidence data, and we can calculate the incidence and mortality data for each county, and then we could model each county looking at these factors. Okay? Everybody follow me so far? Okay. And then we use county level z-score averaged by health district to look at the health outcomes. Greater risk for worse health outcomes than average Georgia counties, where there was a positive z-score, and a negative z-score meant there was lower risk. And we mapped by health district, and we did a correlation analysis between z-scores and the mortality incidence ratios by health district. So here are the data. We had 186,000 incident cancers and 71,000 cancer deaths for the state of Georgia over that time period. We had a geographic GIS score, and so we only were able to use the data that actually had a good address, right? And then we mapped each one of those, right? So we knew the exact location within the census tracts and counties for each of these cancers. And then we calculated the rates. I'm sorry, this is probably hard to see in the back. I'll go over this. But this is the mortality incidence ratios. So this is for blacks and whites. So the mortality incidence ratio for all sites combined for women was 0.44, so 44% basically, and it had a certain confidence interval that we calculated. For men it was 0.47, but you can see for whites the mortality incidence ratio is 0.37 for women and 0.43. So you can see that they're lower in whites than in blacks. This black-white ratio over here is the ratio of these mortality incidence ratios. So you can see that for every single cancer site, the ratio is over 1, which means that the mortality incidence ratio is higher in blacks than in whites for every single cancer site, right? And here for breast cancer, it's 0.25. For blacks, it's 0.18, and the black-white ratio is 1.4, so 40% higher mortality to incidence ratio for breast cancer in black women compared to white women, right? And we go down here to lung, and whites compared to blacks, black men, it's pretty similar, really. There wasn't much different for lung cancer. For oral cavity cancer, though, you can see that it's 0.398, 0.220 for men, black men versus white men. The black-white ratio is 1.8, so 80% higher mortality for oral cancer in blacks than in whites, men. Right? All right, and prostate cancer is a huge problem in the United States for black men. You can see that the 0.24 is the mortality incidence ratio. Usually prostate cancer doesn't kill people, right? So it's a high incident, but usually not high mortality. So 24% versus 15% in whites, but it's 1.6 is the mortality incidence ratio, or the black-white ratio, right? So, what's nice about the measure is that it adjusts the, so it looks at mortality adjusting for the incidence level. And so we did different mapping cutoff points for the mean MIR for whites nationally was the reference. So what we said is, okay, let's look at the MIR and let's map the MIR in each of these groups relative to whites, okay? And if it's 10% higher, we gave it a certain color. If it's 20%, upper bound was 20%, 10 to 20. If it's greater than 20% was category 4. Okay, so 20% higher than the white rate nationally. So we were interested in how Georgia compared to the national rates. So here's the maps. So again, it shows you how you can take maps and display information. So this is, let me walk you through this. This is all-cause sites, mortality in inches. So this is age-adjusted all cancer for white males to the national mean for the MIR. And so the blue is category 4, where it's greater than 20% higher. And this is the all-cause mortality incidence ratio for black males. So this is white males, black males. So, and this is again relative to whites nationally, okay? So you can see that there's these patterns where we see high mortality to incidence ratios compared to the national figures. So what's really great is because then we can take these health districts and say, what's the problem there? Why is there much higher mortality given the incidence? Is it access to care? Is it treatment? Is it late stage at diagnosis? What is it? What's driving that? Okay. So it's very provocative to look at these maps and say, oh, wow, you know, where are the issues? Where are the problems, right? And here's female breast cancer mortality. This is for whites. So you can see that for white female breast cancer, there's just this little area that's in the category 3. But look at this is again female breast cancer among blacks compared to the national figure for whites, and just about the whole state is in category 4, right? So huge problems with regard to mortality given the incidence for black females in Georgia. Here's lung cancer. Again, lung cancer wasn't a big an issue, right, compared to the other. But lung cancer, again, once you get lung cancer, it's a pretty deadly disease, right? So it really kind of doesn't matter even the stage of diagnosis, because they're all diagnosed at later stages. And here's prostate cancer. Again, there's this pattern, this belt in the inner part of the state. For category 4 for whites, but look at the blacks. The black mortality from prostate cancer compared to the national figure for whites is all blue, greater than 20%, right? Yes? Sorry, say it again? Well, it's stage of diagnosis. It could be access to health care and treatment, right? Different treatment. Yes. So one of the things we had is access to care, right, data, and then we did these correlation coefficients between health district factors. So here's health behavior. So we came up with certain, I have the published paper, we can give you the paper, but one of the nice things we could do is actually take and look at the significant correlations. So for all sites combined, we found significant correlation, and for lung and bronchus, again, this is for the health behavior, which is mostly smoking, which is driving this, right? The smoking rates. So lung cancer came up here, and then you can even map that, right? The correlations between the health behaviors. So tobacco use, diet, and exercise is top left. Socioeconomic factors, physical environment. So just to show you that some of the things you can do. I mean, there's not enough time here to go over each of these maps, but to show you kind of the value of then taking that information and display it geographically to generate, and this is kind of generating hypotheses about what may be happening with cancer in Georgia. So now we want to design analytic studies to say we need to look at breast cancer in black women in Georgia. Is it the fact that maybe they get triple negative breast cancer, or the type of breast cancer, that sort of stuff. Is it access to care? What are the issues driving this geographic distribution? County health rankings and use of health districts. The MIR is efficient, avoids survival studies. So it's really a neat measure to use. Larger MIR for blacks, more fatal cancers in West and East Central Georgia, and it may be related to health behavior, clinical care, socioeconomic factors. Now, how much time do we have? 20 minutes for Steve. And just to give you a few preliminary slides, and then Steve's going to talk about our analysis of different cancers in Georgia related to some measured environmental factors. So this is uranium sample points. So we had groundwater sampling of uranium actually in the water. There's a lot of granite tracks, right? And then this is they predicted, so using kriging and using GIS, it takes all the measured levels in all of these points, and you can see that there's significant patterns where the groundwater uranium is much higher, right? And the concentrations are way above, in these darker areas, are way above the standards for safe drinking water, okay? And then we did the same, so we had measured radon from the houses. where people get the little disc, right, and you put it in your house and you can measure how much radon gas is in your house. So we took all of the data for Georgia and we did the same thing using Kriging and GIS methods. This is the high exposure areas. The red is the high exposure. Here's the colors, right, in terms of the exposures. And 4, is it 4 is the standard, I think? 4 microcuries is the high. So the red areas and the tan areas are. So this is the predicted as picocuries per liter. So there were some really high areas. And then this is the age and stratified relationship of log transform radon concentrations by county and cancer incidence. And so we had adjusted models adjusting for gender, race, tumor stage, county level median household income. And so we looked at lung, kidney, and renal pelvis. Female breast cancer, again, unadjusted was 1.1, but when we adjusted for these factors, we really didn't find any significant difference in the radon. This is radon concentrations. So this gives you an idea of the type of stuff that can be done. Now, Steve's going to come up and talk to you about some of the ways. So we took that was just kind of a preliminary test of a certain geographic area. So he's going to tell you a little bit about some of the modeling procedures that he's developing to take a look at these data in terms of how do we take the incidence data in Georgia for all those sites and relate it to those concentrations of exposures over space.
Thanks, John. Let's see, make sure I find, there's the buttons. I'm going to tell you a little more about the statistical or biostatistical end of this, and I'm a spatial statistician by training and have worked in this area for some time. The data that John was just describing is characterized by having a number of different layers. In fact, if you look at most geographic information systems, you're really trying to do analyses using a number of different data layers, and this is true for this project as well. So the layers are the main layers are the cancer data themselves, the some individual level covariates such as age, gender, and race of the subjects. We also have some radionuclide data, radon and uranium, as John just described, as well as some geologic data as useful essential covariate data. This first slide here looks at the different cancer layer indicators, and what we have is actually the point locations of subjects who had bladder, breast, colorectal, and so on, different types of cancers, and we also have this other category which covers a lot of the more rarer cancers, but there's actually a pretty substantial number of those in this data set. So for each of these cancers, we actually have the point locations. What we're really lacking in this particular study is the locations of any controls. And so there's some difficulties in terms of looking at population patterns in the state. Population densities certainly affect where you see the cancerification. You're going to generally see more cancers where you have more people. So that's one of the things we have to work with. So this is the first data layer. We also have radionuclide data. This is the groundwater uranium. This is measured in a number of different wells scattered throughout the state. And you can see here that there's a very large number of sites here where data are collected. The other one we have here for radionuclides is the radon data. This is, as John indicated, is collected in households. One of the characteristics here is that none of these data are collected at exactly the same sites. So we have the cancer data collected at the sites where the patients are. We have wells somewhere else, and we have the radon in the houses yet somewhere else. So these data are so-called spatially misaligned, And this offers a number of challenges to data analysis. And one of the primary problems, I think, in environmental epidemiology is really to get a good indication of what people are exposed to. Yeah, theoretically, you can put some kind of monitor on somebody's back and have them live with it for their lifetime, but who's going to do that? So there are very strong limitations on how you can measure exposures, and that has an impact on the data analysis, generally weakening the analysis. Usually it won't tend to cause false positives, it would tend to shrink estimates towards zero. One of the helpful things is this third data layer, which is really at a different kind of spatial scale. This is a map showing locations of geologic regions. Turns out radiation measurements tend to be related to the geology, how much granite there is in the rocks, and so on. So what you have here is in these regions in northeastern Georgia, rather, where you tend to have rock types that tend to have lots of granite, and you tend to have a lot more radiation than you would have here in southern Georgia, where you don't have exposure to those types of rocks. So the approach that I'm going to describe very briefly, I'm not going to get into any details, I don't have time for this, but we're working with a Bayesian hierarchical geospatial model. And this is built in many stages, and in several stages. The model I'm going to describe here today is a three-stage model. One could conceivably have many more stages than this, but the same general principles will be applied. The more stages you have, generally the more computationally cumbersome it's going to be. It's going to tend to be a lot more computationally intensive. So we're looking at three stages that and all these are going to be linked together. We're going to have a geospatial model for the radionuclide levels. So this is the kriging that John was talking about earlier. And tomorrow during the workshop, I'm going to go over what kriging is and how you do it, what it's all about, and talk about how you turn it into a Bayesian methodology. That's part of what I'm going to talk about then. So that's the first stage, is the geostatistical model there. We're going to use that geostatistical model to predict, but with error, the radiation levels at the households where the cancer cases are found. And then we'll look at a logistic regression model for the pattern of the cancers themselves, essentially conditional on the demographic characteristics of the subjects, as well as the predicted levels of the radiation variables, radon and uranium. Since this is a Bayesian methodology, we also have a prior model. I generally use a very non-informative prior. There's a lot of question as to, well, I don't know how many of you know what Bayesian methods are about. There's some question as to whether and when you should use those, but one of the weaknesses in spatial statistics is that the non-Bayesian methods do not tend to take into account variation due to the estimation of the correlation structure when it comes down to getting standard errors of your parameter estimates. So there's this important source of variation that's ignored, whereas the Bayesian methods readily do take this into account. And this is one of the main reasons why I do this. The other thing is trying to do anything frequentist here in terms of the theory is really a mess. I mean, it's an untidy, messy exercise. And a formula I can't fit on a big page of newsprint and things like that, so it's really difficult to work with. So it's generally these Bayesian approaches are easily worked with, relatively easily worked with. I'm going to describe some of this, a little bit about the stages. What we have is a geostatistical model for the radon levels, and here Z is the radionuclide location written as a function of location S. So here throughout my slides, S is essentially shorthand for the XY coordinate of the site. The model includes a mean here that depends on the geology. So each location is categorized into different rock types, and here this subscript I is used to denote which rock type I'm working with. The errors are going to be spatially correlated. This is our covariance spatial covariance function that we're using. This is the standard exponential covariance function. There are a number of choices available here. In this case, this one seemed to work pretty reasonably well. I'll talk more about correlation functions, spatial correlation tomorrow. It includes a nugget effect, which essentially you can think of as an indicator of measurement error. We have a logistic regression model for the cancer data. And here's essentially how we're going to proceed. If you had a case control study set up, typically, this is an approach that Peter Diggle likes to use in Britain. Typically, he uses an intensity function which describes essentially the local population density, if you like, as a function of location. Here I'm using U for location. So this is going to be like a baseline measure of population density. And if you're looking at the cancer cases, we typically use a similar kind of intensity function or baseline local population density. But this is now can be adjusted for various covariates. So the covariates here are denoted by this X. We have regression coefficients beta. And the X's can include things like age and gender and racial group, and as well as the radionuclide values. So this is what we're using. And it turns out if both of these are realized from so-called Poisson processes, it turns out that the cancer indicator, whether or not you're looking at a cancer case at a location or a control at a location, can essentially be modeled using a pretty standard logistic regression. Here's our setup for the logistic regression. It just gives you this beta transpose X just like we have in there. So this turns out to work. This is something that Peter Diggle showed some time ago, and I recently published a paper saying that this is the right thing to do. Actually, it's the optimal thing to do. So that's what we're working with there. There's a prior model. I'm not going to say much about the prior model here. It's just I'm trying to be somewhat non-informative so that I don't want my prior choices to influence too strongly the results here. This is somewhat technical. We can go over this in more detail at some other point. That's just more about the prior model. Okay, so that's the basic model we're working with. The issue we're trying to deal with, however, is this spatial misalignment. The cancer cases are not at the same places as the measurements. This is something that's been looked at by a number of other authors. Here's some references to that. And many of these other studies are distinct from the study I'm working with in that the cancer cases are aggregated by various political units like counties or zip codes and so on. In this case, in our data case, we actually have the locations themselves. So that's one area this differs in. One of the problems with the data aggregation is the so-called ecological bias. If you basically aggregate the data, you often find patterns that are very different than what you might get if you actually had the point data. Okay, so one of the things we're trying to avoid here is this ecological bias. And one of the things we can potentially explore with these data is how much ecological bias we have, but that will have to be left for a later time. I'm not going to I don't have time for this detail, so we'll skip this. We use a computationally Monte Carlo Markov chain algorithm to do the statistical inference. This is some of the details. It includes the data augmentation algorithm, and but I'm not going to get into that. We're taking a two-stage approach to this. We're not using a fully Bayesian approach, which tends to be much too computationally cumbersome. So we're taking a two-stage approach, which basically entails, to some extent, separate workings with the geostatistical model and the logistic regression model. There are a couple versions of two stages approaches one can take. One which allows some feedback between the health outcomes and the exposure estimates. And you could potentially allow some different levels of feedback. In this case, I'm using feedback between the health outcome and the exposure estimates at the individual sites. We use 4 different rock types. I'm going to show the results for just uranium exposure, and I'm going to control for age here. And oh yes, this is delayed because we didn't run it before. I probably should have cut this slide out and make sure. There it comes. Yeah, there it is. So basically, you run these simulations, and here you can see it's run out for 60,000 iterations. So you do this for a large number of iterations. You get a lot of noisy-looking patterns. In fact, this is what you want to see when you're doing these. Just pure noisy mess is what you really want to see. This describes the correlation structure of the simulations. I'm not going to go into that. But what you have here is basically adjusted odds ratios for the different cancers. And basically what we're doing here is comparing the different cancers, in this case, to the other cancers. Okay? We don't actually have the controls in this data set. If there's nothing going on at all these odds ratios for the impact of uranium exposure should be about equal to 1. And you can see they are not. Although most of the confidence intervals do, well, I guess they all do include 1, but there are some that are kind of close to some significance on the protective side, actually, more than anything for bladder cancer. Seems to show less effect of the radiation than the remaining ones. It doesn't seem to matter much as to whether you use feedback or not. The results were very similar, the estimates were very similar, confidence intervals were similar. The nice thing about this is that the model without, the procedure without the feedback is much faster. It proceeds much more quickly than one with the feedback and is much easier to program as it happens. And so this is the main results, and I think I'm pretty much out of time.
This is the preliminary results for that, just that one little geographic area.
Yeah, we're looking at the one geographic area.
On the one map, there was a little red square, so we just took one little geographic area just to pre-test this before we ran it on the full state data. So the full state data, with all of the data, will be much more robust.
Yes.
We just wanted to test the model before we ran them on the whole.
Yeah, this is very much work in progress. There are a number of additional challenges that we're going to be looking at here. These models I'm sort of building step by step. One of the challenges is that the radon levels are actually so-called left censored. There are a number of values where no radon radiation were actually detected. There's basically a detection limit below which you essentially know it's between 0 and that limit somewhere. And actually, one should take that into account. And there's substantial censoring in the radon values. There's a method that de Oliveira came up with some time ago, a Bayesian approach that we could apply here. I've also done a non-Bayesian approach myself and published, but we'll get into that. One of the significant challenges, however, is a very, very large number of radon and uranium observations. It offers considerable challenges to these Bayesian methodologies. And we're looking at some various approaches to dealing with these large data sets. And it's one of the things that's delayed our full implementation. So I think that's about all I have here, but I guess we can both take questions.